Hi everybody, this is Tim Urdan, author of Statistics in Plain English, and in this video what we're going to do is compare two sample correlation coefficients to see if they are significantly different from each other. And what we're testing here really is this null and alternative hypothesis, which says, are the population correlation coefficients of these two populations that the samples represent, are they equal to each other, or the alternative that they're not equal to each other? And in this case, suppose that I have two samples of men and women, and there are 100 cases in each sample. And I'm looking to see what the correlation is between the amount of time they spend studying before a test and the scores that they get on the test. So for the sample of men, the correlation between amount of time studying and scores on the test is 0.30. And for women, the correlation is 0.50. Now I want to see whether those two correlation coefficients are significantly different from each other. So, first thing that we have to do is transform these correlation coefficients using the Fischer Z transformation so that we can get these coefficients onto a normally distributed scale. That'll allow us to then compare z-scores or calculate a z-score and see whether it's statistically significant. So let's transform these using a Fischer Z transformation. You can look in Appendix E to find that transformation, or you can use an applet that you find on the web. I have provided the link to one of those applets in the book, and so I'm going to show you how to do it using that applet. All right, so the correlation coefficient for the sample of men was 0.30, and the Fischer Z transformation of that is 0.310. And the correlation coefficient for a sample of women was 0.50, and the transformation of that is 0.549. Okay, so the Fischer Z transformation of the correlation coefficient for men ended up being 0.31, and for women it was 0.549. Make that 3.310. All right. So we have our Z prime numbers and we know our sample sizes. So now we just have to take this formula and plug in the numbers. So we're trying to calculate a z-score, and we plug the numbers in. We say 0.30, noops, that's not right, sorry. Say 0.310 minus 0.549, that's the numerator. The denominator is the square root of 1 over 97 plus 1 over 97. So we have negative 0.239 in the numerator, and the square root of 2 over 97, and the square root of 2/97 is 0.1 4. And then when we divide the numerator, 0.239 divided by 0.14, we get 1.707, which will round to 0.1, and that's a negative number. So that is our z-score. Now, for that z-score to be statistically significant, it would need to exceed our critical z-value. And when I say exceed, I mean it would need to be bigger than the positive number or smaller than the negative number. Exceed meaning it would need to be beyond it. So if that is our normal distribution, just pretend that's normal. And these are our two critical z-scores. Our observed z-score would need to be in these darkened regions. It would need to exceed these critical numbers. Our observed z-score is right there. And as you can see, it doesn't exceed it. So now we are ready to reach a conclusion. Because our observed z-value does not exceed our critical z-value, we retain the null hypothesis and conclude that these correlation coefficients are equal in the populations of men and women. There's no difference between the correlation coefficient of men and the correlation coefficient of women in the populations. And that's how you do it. That is how you compare two correlation coefficients from samples. Hope that's helpful.